In this video, we're going to look at small covalent molecules, and we're going to learn how to represent them as a Lewis dot structure and also write an accompanying formal charge table for the structure. So here we have three species. We have water molecule, we have carbon dioxide, and we have an ammonia molecule. These are three canonical species that have great biological significance, and most often these will be the three first molecules that you study as a chemist. To write the Lewis structure, we identify the central atom. Now the central atom is the atom in least abundance. So here we can see we have hydrogen and oxygen in a 2-to-1 ratio. So oxygen, having only one out of the 2-to-1 ratio, is in the least abundance. We write the central atom for water here, and then we surround it with the non-central atoms, which in this case are hydrogen. We now connect everything once, because everything is connected at least once in a molecule. And here we're assuming that the line or the covalent bond represents 2 electrons. I now have to write the formal charge table. The formal charge table is going to have several lines. The first line is the constituent elements. So in this molecule, I have 2 hydrogens and an oxygen. The second line of my formal charge table, I have to write the number of valence electrons. So if I look at my periodic table, hydrogen is in group 1, it's got 1 electron, and that electron is valent. Oxygen is in group 16, it's the 6th main group, it's got 6 valence electrons, so we write 6 here. We then add these valence electrons up, so 1 plus 1 plus 6. So I know that a water molecule has 8 valence electrons total, and I have to make sure I have 8 valence electrons on my structure. If I go back, I've only represented 4 electrons so far. Remember, each line is 2 electrons. So I've got 2 electrons here and 2 electrons here. That's 4 electrons total. So I've got to add an extra 4 electrons. I cannot make a double bond because hydrogen is incapable of making a double bond. It can only make 1 bond. So I put them as 2 lone pairs of electrons on the central atom. Why the central atom? Well, again, hydrogen can't accept any more electrons than it already has. And also, oxygen is more electronegative. It has a greater pull for electrons than does hydrogen. So oxygen benefits from the extra electrons. Now I've assigned electrons, I have to analyze how I've assigned them. The next line on my formal charge table, I look at bonding electrons, these lines, and non-bonding or lone pair electrons, which are the dots. Hydrogen has 1 line, that's 2 electrons, and you get to keep 50% of all of the line electrons. So 1 line, 2 electrons, 50% of that is 1. Likewise for this hydrogen here, 1 line, 2 electrons, 50% is 1. Oxygen has 2 lines, that's 4 electrons, 50% of 4 is 2. But you also get to keep all of your dot electrons, so 2 plus 4 is 6. And now finally the formal charge is the top number minus the bottom number. So 1 minus 1 is 0, 1 minus 1 is 0, 6 minus 6 is 0. So the formal charges of all of my elements in a water molecule are 0. This typically signifies a stable molecule, and we know that water is stable. If you were to add the formal charges, it also tells me that water is a neutral molecule, because the sum of the formal charges is 0. Comment at this point that the Lewis structure has no shape representation whatsoever. Water does not look like this, other than the fact that water does have 2 hydrogens, 1 oxygen, 2 bonding pairs, and 2 lone pairs. But there's no bond angle representation intended here. Okay, So let's move on to carbon dioxide. Carbon dioxide, we identify the central atom as carbon because there's fewer of them. We then surround it with the non-central atoms, in this case our oxygen. We just try and separate everything as far as we can at this point, but we acknowledge no bond angle representation. We connect everything once, because everything is connected at least once, and then we start writing our formal charge table. I have carbon and 2 oxygens. Carbon is in group 14, so it has 4 valence electrons. Oxygen is in group 16. It has 6 valence electrons. And if we add these together, we can see that there are 16 valence electrons total. I've only represented 4 electrons right now, so I have to add an extra 12 electrons, and I do so as lone pairs initially to the most electronegative element, which in this case is oxygen. So oxygen has a greater ability to pull electrons, so when electrons are added, carbon loses out and oxygen pulls them in. So I should have 16. I've got 6 dots over here, 12 dots total with these extra dots, and then I have my extra 4 line electrons here. So I have 16 electrons. Everything looks okay, except one of the guiding principles of S and P block chemistry is that elements want to combine. They want to share electrons in a covalent compound to become isoelectronic with their noble gas. So whereas oxygen has achieved this, oxygen now has access to 8 electrons total. So oxygen is behaving as if it's isoelectronic with neon. Carbon only has access to 4 electrons, so carbon is isoelectronic with no one. So what we're going to do, we're going to take a lone pair away and we're going to reconstitute them as a bonding pair. If we do that on the other side also, so we haven't added or subtracted anything, we've just redistributed what we had. Now carbon has access to 8 electrons, so does oxygen, and so does oxygen. So now all members of this compound are isoelectronic with their noble gas, which in this case is neon. Carbon now has access to 4 lines. Each line is 2 electrons. 50% of those 8 electrons are now 4. The oxygens are identical, so let's look at one of them. Oxygen has 2 lines, that's 4 electrons. 50% of 4 is 2. Plus you have 4 dots, so that's 6. And the top number minus the bottom number is the formal charge. So 0 formal charges, we know that CO2 is stable. And the sum of the formal charges is 0, so we know that carbon dioxide is a neutral molecule. And finally for this set, let's look at ammonia. Ammonia has nitrogen as the central atom. And I'm going to surround this, try and separate them, although there is no shape representation, with the non-central atoms, which are hydrogen here, and we'll connect everything once. Nitrogen, hydrogen, hydrogen, hydrogen. I've got 5 electrons, 5 valence electrons for nitrogen, 1 valence electron for each oxygen, and I've got 8 valence electrons total. I've only represented 6 electrons as it stands. I can't add any more electrons to hydrogen. So my final 2 electrons to give me 8 total must be a lone pair on nitrogen, which makes sense because nitrogen has a higher electronegativity than hydrogen and therefore can pull electrons to a greater degree when they're available. Each hydrogen now has 1 line, that's 2 electrons, 50% is 1. The nitrogen has 3 lines, that's 6 electrons, 50% is 3, plus the 2 dots is 5. The top number minus the bottom number is the formal charge. They're all 0, so I know that ammonia seems to be a stable compound. And the sum of the formal charges is 0. meaning that ammonia is also a neutral compound. So these are three canonical small molecules. We've gone from the species to the Lewis structure, which has no shape representation whatsoever, and we've done a concomitant or a joint formal charge table, which essentially is used to help validate the Lewis structure.